And over to you.
Okay, thank you. Hello, everybody, and welcome to Team 10's presentation of HelioGEAR, also standing for Green Energy Accurately Reflected. Thank you for being here. We are excited to walk you all through our small-scale heliostat design. To begin, I'd like to introduce my team. My name is Julia St. Hilaire.
And I'm Sammy Ghazi.
I'm Katie Lara.
I'm David Norton.
My name is Trevor Noyes.
I'm Jeremy Rutenberg.
And I'm Rudy Oliva.
And we are Team 10. So just as an overview for this presentation, we will go over the hedgehog concept and driving factors next, followed by the product overview, design highlights, and key features. Then the subsystem analyses for our 4 selected subsystems, which are actuation, reflectors, support, and electronics. After that, we will go over our cost breakdown. Then we will wrap it up and have time to answer any questions.
So one of the first steps that the HelioGEAR team took to converge on a final conceptual design was developing a hedgehog concept. To do this, we had to examine 3 important questions. Firstly, what our team was best at. Secondly, what our team was passionate about. And thirdly, what drove our economic engine. After some careful deliberation, we determined that our team was best at combining our mechanical engineering skill sets to solve complex problems using innovative solutions within the field of mechanical engineering. Secondly, we determined that our passion lies within using the innovative solutions we developed to make clean, renewable energy economical. Finally, we needed to figure out how to make what we were good at and passionate about unique and profitable for our customer. Our goal was to increase the profit margin per unit of energy collected by our heliostat module. To accomplish this, we aimed for a strong, low-cost design that had minimal tracking error to reflect more of the collected light onto the receiving target. With the ever-changing status of the world market, it allowed us the ability to utilize unconventional, low-cost, and high-strength materials to keep the overall module cost down. To further increase the efficiency of the design, the HelioGEAR team aimed to create a design that required minimal maintenance for the full 20-year service lifespan of the module. Conceptualizing these thoughtful diagram, we find the HelioGEAR module right at the very center.
Next, we'll go over just a broad product overview of HelioGEAR. To begin, you can see we have a model of the finished product. HelioGEAR will encompass 4 subsystems that are shown on the screen: the reflector subsystem, actuation, support, and electronics. The reflector subsystem will utilize 4 mirrors for a total reflective area of 1 meter squared, while also encompassing a reflective mylar film surface. Next, the actuation subsystem will utilize 2 different types of motors for the 2 different axes, azimuthal and elevation. The azimuthal motor will utilize a bipolar stepper motor, while for the elevation axis, we'll use a NEMA 17 stepper motor. Furthermore, the support subsystem will feature a main support PVC pole that you can see in the middle there, and then also a support crossbar that the mirrors will essentially be connected to. Lastly, the electronics will be composed of an ESP32 chip for Wi-Fi and Bluetooth connection, while also looking at having a limit switch that will be attached to the PVC pipe to alert the system when the mirror is not at its home position. Next, based off of the product overview, some of the highlights and key features from those were taken away to be the PVC support system, the geared actuation mechanism, and utilizing the mylar for the coated surface on the mirrors. The PVC support allows us to achieve very lightweight, rigid, and long-lasting structure for a minimal cost. Moving on to the geared actuation mechanism, Utilizing these gear sets that are very specific to our concept allows for extremely precise tracking of the sun and results in minimal loss of reflected sunlight. And finally, the Mylar film coated surface. These create for a much stronger, more durable mirror for even a less cost than one would think for a conventional glass mirror. And now we'll take a look at the actuation subsystem.
Okay, I'd like to wish our guests a warm welcome. Good morning. So this is our actuation system. So we have 5 individual motors that will be controlling our system in 2 dimensions. We have a large azimuthal motor that has 17 foot-pounds of torque and 4 vertical stepper motors, each with 0.35 pounds of torque. In order to control the surfaces, we're using different geared systems. So the azimuthal motor is very high in torque, and it uses a relatively smaller gear than the vertical motors, because as we'll see in a moment, the vertical motors use very large ring gears, and the azimuthal motor, because of geometric constraints, uses a slightly smaller ring gear. So the azimuthal control is done with a single motor, and this is energy efficient and allows all 4 mirrors to rotate in the horizontal plane at once. But each mirror can be rotated in the vertical dimension on its own. If we could see the next slide, please. Thank you. So we have an exploded view and an isometric view of the actuation subsystem here. So if you'll take a look on the left, the control case is made of PVC. We have the, I'm sorry, not PVC, excuse me. It's 3D printed and made of PLA. We have a PVC support in the center, a 3D printed ring gear, the azimuthal stepper motor, motor mounts, various fasteners, and some minor other parts. This large gear in the center, I'm sorry, one moment. This large gear in the center uses a reduction ratio of approximately 2.8 to 1. And this gives the required torque in order to rotate the whole system. Now, as you probably noticed from the last slide, it is a bit T-shaped. So that requires a lot of torque to be able to rotate the entire system at once. Next slide, please. Okay, so here we have the second part of the actuation subsystem. We have an exploded and isometric view of the vertical actuation subsystem. So we have the NEMA 17 stepper motor, which has less torque than the previous stepper motor. In turn, there is a larger gear ratio of approximately 6.5 to 1. We have our PLA 3D printed gears, our PLA 3D printed gear coverings to protect from the elements, some custom motor mounts. And this is all designed to help the system rotate accurately with minimal error and with maximum longevity. Next slide, please.
All right, so here we have for the customer needs that were grouped into the actuation subsystem, and it stems from what the customer need is and how we were able to map that ultimately to a design function. The 4 major customer needs for the actuation subsystem were found to be that 1, each module needs to mitigate optical losses due to tracking errors not to exceed 40%. And with our geared actuation design, we are able to control very precise movements of the heliostat. So we have 0 tracking error. Next, the heliostat must be capable of tracking the sun throughout the day. In order to do so, there needs to be at least 2 degrees of freedom. And thus, in our concept, HelioGEAR rotates both azimuthally and vertically to get those 2 degrees of freedom. Next to capable of redirecting sunlight to a central tower up to 100 meters tall. We found that the vertical rotational movement must be greater than at least 90 degrees. And with our design, we have a vertical rotation movement of a minimum 180 degrees. Next, the operational lifetime of at least 20 years. Our design is designed to last the entire 20-year service lifespan while looking at all of the factors of, use in Las Vegas, Nevada under certain extreme conditions.
Okay.
Sorry, go ahead.
Thank you. Furthermore, we have some critical analyses of the actuation subsystem. So on the left, we have tracking error. And obviously tracking error is a very important aspect of this design. So initially we looked at many different factors that would go into tracking error and specifics to Las Vegas, Nevada. We look at some boundary conditions such as where will the sun be on the most extreme cases, such as early in the morning, late in the evening, and during the winter solstice. That was when we determined that the sun would be the lowest during operating conditions. But effectively, for this analysis, we assumed that the sun would be moving 180 degrees across the sky over 12 hours for simplicity and general accuracy. And this yields an angular rate of 0.25 degrees per minute. Using that, we can plot the optical gain against the angle of incidence between the sun and the actuator. So the optical gain of the system when we do this is 50%, and the optical losses due to tracking are 50%. This doesn't meet the threshold that the customer requires of 40%. So we can use this model to develop a linear relationship between the size of the increment and the optical loss. And when we do this, a second boundary condition is needed. And because the sun was previously assumed to move at an angular velocity of 2.5% per minute, an actuator that can increment by this amount, we're going to assume has an optical loss of 0%. And from these two conditions, we can find like a linear relationship where theta sub A, as we can see in the diagram, is the minimum rotational increment in degrees that the actuator can produce. So when we put all of this together, that means that the optical losses are very near zero because we're using very high gear ratios, very precise gears, and very precise stepper motors. So when we look at the vertical motion ability on the right, we want to reach a height of 100 meters on a target tower. Some of the heliostats will be very close to the tower, some will be at the edge of the field. But no matter where the heliostat is on the field, there's going to be a change of elevation by at least about 76 degrees. So the angle between the heliostat and the receiver would be noted as omega in this case. We have omega 1 and omega 2. And the mirrors are actually able to rotate a full 180 degrees because of how the gears are designed.
So shown here is the final design that we came up with for the reflector subsystem. We ended up going with a design that incorporates 4 rectangular mirrors per module, each having dimensions of 0.25 meters by 1 meter. This brings the total reflective area per module to 1 square meter. The mirror surface that you see in the model is not actually the mirror, but just the support back. The reflective material we went with is a mylar film due to its low cost, low weight, and high reflectivity, higher than regular glass mirrors. The support backing for the mylar film is actually 15 32-inch boards of pressure treated plywood. Initially, we designed this backing to be made out of injection molded ABS plastic, but with a cost of nearly $300 per module, this was ruled out as being far too expensive. The mylar film will be attached to the wooden support through the use of a spray adhesive. The mirrors are actuated by stepper motors connected through a gear track at a reduction ratio of 6.5 to 1. So this really tall gear ratio allows for the tracking to be very accurate. For each step of the motors, the mirrors actually only shift 0.3 of a degree. Initially, the gears were going to be exposed and machined out of aluminum. However, through several design changes and attempts to save costs, the gears were changed to be 3D printed out of PLA. As a result, it became a concern that sand and other debris could become trapped in between the gear teeth and over time wear down the plastic and cause the gear system to become loose, reducing the accuracy of the tracking. To fix this potential problem, gear covers, also 3D printed out of PLA, were designed to fit snugly over the gears to minimize the sand and other debris that gets in between the gear and the gear tracks. This entire system is held up by the 2 hinge rods that you see on either end of the mirror supports, which are 3D printed out of PLA plastic as well. They slip onto the ends of the wooden backing and are fixed to the main support system through the use of 1/2-inch steel bolts through the crossbar. On the next slide. So yeah, this next slide shows how the subassembly how the subsystem is assembled. So basically, the gear track is aligned with the longitudinal axis of the wooden mirror support, and it's fixed in place so that it's concentric with the axis of rotation of the mirror support. While the hinge rods do not rigidly attach to the wooden support, they are fixed in place on the crossbar and keep the mirror in place from sliding off of the ends of it. After the heliostat has been fully assembled with the elevation motors in place, the gear covers are added by aligning them with the gears and using self-tappers to fix them to the mirror support.
This next slide is in regards to HelioGEAR's reflective subsystem customer needs. As we can see, based on the customer needs statement that we received from the proposal, we determined that many of the customer needs did in fact relate to the reflector subsystem, making it one of the most important subsystems. Beginning at the top, customer need 1 asked us to address innovation by small heliostat size. This was a metric that was hard to define quantitatively. However, the way we chose to do it was by essentially taking the highest average from the combined module cost, shading, and focal inputs from our conceptual designs. So we combined all of those together to create the best functional design to allow the heliostat to be innovative by small size. Secondly, the total reflector collection area had to be equal to or less than 1 square meter. HelioGEAR is able to fulfill this design need by utilizing a mirror system that has 4 1/4 square meter mirrors to add to a total of 1 square meter of reflective surface area. Third, each module needed to be composed of 4 to 16 heliostats. Our final reflector subsystem utilizes exactly 4 individually controlled heliostats. The 6th customer need asked us to basically make sure that the heliostat module could not shade other modules. So we performed an analysis on this and were able to determine that in order for 0 shading to take place from the HelioGEAR module to other HelioGEAR modules in the field, they needed to be spaced 4.5 feet apart, which was far less than our quantitative metric of 10 feet. Customer need number 8 says aggregate cost must be less than $100 per square meter of reflective service. The final design cost for this module came just under $300. We got it down to around the $270 mark per square meter. So we definitely were not able to meet the customer need in this respect. However, we do have some analysis later on to explain why this was not the case. Customer need 12 asked for the surface to be washable using conventional washing techniques. So we performed a reactivity analysis on HelioGEAR's reflective Mylar surface to ensure that the Mylar would not be reactive with any of the conventional cleaning and washing techniques. Customer need 17 asked for a focal thermal input of 1 megawatt of energy And the HelioGEAR has a thermal input power of actually far greater than a megawatt. It's nearly 2 megawatts. So customer need number 18 asked for a solar concentration ratio greater than 1,000 suns, and the HelioGEAR module is able to deliver a solar concentration ratio about 2,200 suns. So explaining this further, the customer needs statement called for a heliostat module to be presented that was able to deliver at least 1 megawatt of thermal input power and have a concentration ratio greater than 1,000 suns. To illustrate, the HelioGEAR module is able to meet analysis for the needs. The analysis begins by writing out the heat transfer energy balance equation and deriving the necessary variables used in the calculation. We determine the total heat flux the heliostat transmits to the receiving tower is the summation of the total heat flux reflected by the field minus the heat flux of the system, essentially the losses coming out of the system due to radiation and scattering from the reflective surface. The heat flux out of the system is composed of the Stefan-Boltzmann's constant, the temperature of the receiver, which we determined to be the average high temperature throughout the entire year, which is that 26.9 degrees Celsius number down there, and the area of the target receiver. The heat flux into the system from the reflectors is composed of the optical efficiency of Mylar, which we determined was 90%. Essentially 90% of light reflected off is further transmitted. This is multiplied by the total number of modules in the field, further multiplied by the radiative heat flux received from the sun and the reflective area of the heliostat module. The solar concentration ratio can then be determined using the heat flux into the system divided by the radiative heat flux from the sun. The next slide shows the completion of the calculations. So completing the calculations gives us a heat flux out, essentially our losses, of 459.57 watts. However, the heat flux coming into the system due to the reflectivity of the mirrors bouncing back to the receiver is 2.79 megawatts, essentially 0.79 times 10 to the 6th power watts. So when we subtract the losses off of this, this still leaves total thermal input of 2.79 megawatts, which is much greater than watt, and a solar concentration ratio that is equal to the equivalent of about 2,040 suns.
Changing gears to the support subsystem. It is mainly composed of a vertical PVC support and a horizontal PVC support. The width of the entire module is 1.3 meters and the height to the axis of rotation is 0.82 meters. The height to the top of the horizontal support is 0.64 meters. Looking at it a little closer, a 2-inch PVC pipe slides into a 3D printed PLA rotator cuff and is held in place by a through bolt and nut. The cuff is press fitted into a 3D printed PLA cuff insert that is press fitted to the steel bearing. That assembly is then press fitted into a 3D printed PLA bearing collar and inserted into the 4-inch PVC main support pole. The main support pole is 9 inches above the ground. Below the ground, represented by the flat plate, is 9 more inches of the PVC main support pole that is driven into the ground.
As our team designed the support subsystem, we primarily focused on the customer needs shown on this slide. Firstly, the customer defined that the factors of safety for the heliostat must be greater than 2. In other words, the support subsystem must be able to withstand at least double the weight that it is intended to hold. HelioGEAR not only met but exceeded this metric with a factor of safety of at least 3.75. Next, to justify manufacturing parts, the customer also required that the cost of manufacturing be less than or equal to that of an equivalent off-the-shelf part. To satisfy this, each manufactured part on the support subsystem is 3D printed from PLA, which is a readily available and easily manufacturable material. On a similar note, the support subsystem is also composed of PVC and steel, both of which are expected to withstand the desert-like conditions of Las Vegas, Nevada. Finally, the ratio of reflective area to the non-reflective area of the support system is 7.3, and when oriented in a field of heliostats about a central tower, the support subsystem positions the reflectors such that the minimum distance between the receiving unit and the reflectors are 98.5 meters.
The bending stress on the 2-inch PVC crossbar was calculated. The crossbar was treated as a cantilever beam from the center pivot point to one end of the pipe. The other half of the crossbar was simply a mirror image of the cantilever beam, resulting in the same bending factor of safety calculation. Therefore, the cantilever beam supported only 2 of the 4 mirror systems. The force from each mirror system was found to be 111 newtons. Using the bending stress calculation, the bending stress was found to be 10.1 megapascals. PVC has a tensile yielding strength of 37.9 megapascals, resulting in a bending factor of safety of 3.75. The buckling factor of safety was calculated for the 4-inch PVC main support. The critical load was found to be 292 kilonewtons, and the applied load was only 467 newtons. So the buckling factor of safety was found to be 626.
The materials of each of the components in the support subsystem were also important in ensuring that the cost and longevity of the heliostat met the needs of the customer. As mentioned previously, the customer specified it and also be able to withstand the harsh rotator cuff insert, and bearing collar all had very specific dimensional requirements that would have been difficult to purchase based off of what the nominal sizing of off-the-shelf parts would have been. The decision to 3D print these components from PLA was due to their low cost and low costs associated with them. Additionally, when considering whether PVC steel and PLA were suitable for operation in Las Vegas, Nevada, we made sure to look up the highest recorded temperature in Las Vegas, which was found to be 118 degrees Fahrenheit, and each of these materials have a maximum operating temperature that is well above that.
Moving on to the electronic subsystem, we chose the ESP32 for the microcontroller. It has universal Wi-Fi and Bluetooth capabilities, and it also is programmable. It has a sufficient operating temperature for Las Vegas and the proper voltage input for the field. We also chose to use stepper motor drivers, more specifically the A4988 drivers. They had a good voltage range as well as many different step resolutions. These also had a sufficient operating temperature. Lastly, we chose to use a snap action limit switch by the brand Omron. Unlike the other electronics, these will be placed on the outside of the PVC crossbar where the reflectors make contact with the bar. This will alert the actuation when the reflectors are fully vertical. It's also worth noting that we plan to use the stepper motors as another source of position management. In the bottom picture there, you can see the limit switch mounted to the PVC pipe where the reflector makes contact. So the rest of the electronics will be placed inside of an electronics box that is mounted onto the PVC main support. This box will be 3D printed and made of PLA plastic, so it will be water resistant. The box will hold the bipolar stepper motor, the ESP32, and the motor drivers. In order to avoid overheating, we have built natural ventilation and convection currents into the box. We also made sure that the electronics could withstand temperatures well above the maximum temperature in Las Vegas. The maximum temperature in Las Vegas was about 47 degrees Celsius, and the lowest electronic maximum temperature is about 70 degrees Celsius. Lastly, we plan to have the wires run through the PVC for further weather protection. We only had one customer need for this subsystem, it being that tracking needed to be computer automated and controlled. We incorporated that into our design by making sure HelioGEAR utilizes the power generated at the field to power the modules. Also, we made sure that all electronics can run on a 12-volt power source.
Okay, so this slide presents a complete cost breakdown for the cost to purchase off-the-shelf parts, raw materials, the manufacturing, assembly, and energy costs for building both a single prototype, as you see in the column in the center, and an entire field of heliostats is the price per heliostat on the right. As you can see, the assembly and manufacturing costs are the same for both cost breakdown, but the majority of the savings for mass production come from bulk savings off-the-shelf parts and raw materials. In most cases, the vendors we sourced offered significant discounts when purchasing items in bulk. In addition to this, some of the cost for a single prototype is wasted on things that can only be purchased in large quantities when only a few parts are actually needed. For example, some of the fasteners used in this design come in packs of 50 or packs of 100 when we only needed 10 or 20 fasteners for a single prototype.
So why do we believe that you should choose HelioGEAR? We believe that our innovative design using unconventional materials allows for a less expensive heliostat module that achieves highly accurate solar tracking. The PVC support system offers a strong yet lightweight design with a high factor of safety. Furthermore, the 3D printed PLA gearing offers precise solar tracking at a fraction of the cost of metal piers. Finally, the Mylar film reflectors offer exceptional reflectivity in a durable package. The HelioGEAR module is designed to have little to no maintenance associated with the design for the entire lifetime of the module. These features make the HelioGEAR solar module an innovative solution to make renewable energy more economical.
In conclusion, HelioGEAR is a well-rounded design with an innovative approach to concentrated solar power. The main focus being the gear-powered actuation system and PVC support, with a total cost of $277 per module if mass-produced. That's it for our presentation. We would like to thank our corporate sponsors, as well as our professors and teaching team. Thank you guys for listening to our presentation. We hope you enjoyed it and got to see all the hard work we put into HelioGEAR. Are there any questions?
So typically, we'd like to let any external guests go first. So that would be Rick Miles or Julia Sander.
So this is Rick Miles, Northrop Grumman. I'll go ahead, but I'm going to kind of pick on one that I know that Julia, if you could. So one of the principal requirements here, if I remember right, is $100 per square meter, and y'all are well beyond that. You know, from a customer standpoint, it would be a hard sell for me to choose your design if you're that far off of where you know the target is. So along those lines, I know you talked about making stuff out of 3D printed material in order to lower cost. Are there any other ways you think that moving forward you could take more cost out of the particular design?
Yeah, so I'll answer that, Rick. That's a great question. One of the most expensive parts in our design right now is the large azimuthal stepper motor. And that's something that we've battled with this entire semester, trying to find a stepper motor that will apply the amount of torque that's required while still allowing the design to function as it's intended. So going forward with more time and research into this, we've looked into different size stepper motors, or possibly even scrapping the stepper motor concept for maybe an AC motor or something like that with a gear reduction to give us the torque that we needed at a much lower cost. So currently that big stepper motor is running us $74 by itself, which is 3/4 of the entire budget. So as far as that goes, that's our major thing that we would like to change going forwards in this design. However, a lot of this does pertain to living in this kind of post-COVID material shortage. All prices are going up. We did a quick financial analysis over some basic materials. Aluminum, steel, plastic, wood, and PVC, which are all materials that we're utilizing in this design. We tracked essentially what the cost of these materials were last year if we were to do this project
Mhm.
versus how they are now. And we're seeing an average material increase of roughly 241%, which is an insanely high increase. And ideally, if we were being able to manufacture this design last year, our total cost would run somewhere about $115 per square meter of reflective surface area. So there's definitely room for improvement, but we're also dealing with some huge financial markups as well.
Okay, so I think that's a great explanation, right? And my apologies, I was tied up in a meeting, so I got here a little bit into your presentation. But if you didn't mention that during the presentation, especially when you get to that cost, I would just kind of make sure to cover that, right? As you knew what the target was, there are some current constraints. There's you would think that potentially there would be a release of those constraints here. And we're not going to be in this inflationary period forever. Right. And so just talk to that, right? You have to go with the data you have now, but you anticipate potential future that cost going down as a result of settling, right? The other thing is if you could go, I think it's the next to last slide, or it's the slide where you show your mirrors going in different directions. That right there. So do you actually expect that that's going to be a case that's going to be valid, right? The sun's always coming from the same direction, right? So why wouldn't all the mirrors be oriented exactly the same way? And if so, could you adjust your actuation so that you're moving all the mirrors in sync?
Yeah, I can answer that for you, Rick. So what you're seeing on the screen, this is actually supposed to be like an animation, just basically showing how all the mirrors can move independently of one another. But unfortunately, we had some issues with the video, so it's just not playing. But you're right, the mirrors for the most part, most of the time would almost be completely lined up. Obviously, each one of them would have slight variations to get the exact right angle. But yeah, they would never really look like this in practice. This was just more of like an exercise of what the model is capable of.
Yeah, so I guess my question is, could you drive down your cost by moving them all together?
So
yeah,
to respond to that question.
Yeah, you can take care of that, Trevor.
So that's something in our conceptual designs that ideally almost every design that we came up with first required us to have a motor in the azimuthal direction that controlled everything. And we would have preferred to have every motor that's rotating in the vertical direction controlled by one motor as well. However, due to one of our customer needs, the customer explained that they wanted the heliostat modules to be individually controlled in at least one axis, which essentially limited us to having to have all of those motors to be able to control them individually in one axis. So ideally, we would have preferred to do it with only two motors, one controlling azimuthal and one controlling vertical. But due to the customer need, we had to submit to that.
Okay, no, that's a good answer. So, and again, this is just my general take, and I know that the professors are somewhat translating the customer needs, right? That's kind of how, but a lot of errors have been made over time by by interpreting customer needs instead of verifying with the customer that that's really what they want. So, at least in the real world, it's something to think about going forward. Is you always want to verify with the customer. If we go with this requirement that you're asking us to do, this is the impact to cost. But if you remove this requirement or just said it was a nice to have instead of a firm requirement, this is the advantage we can get you from a cost perspective. It's always good to have those sort of conversations. The class might not have been set up that way to do those sort of conversations, but just something to think about as you move into other design classes and actually work out in the real world. Never take something provided as the customer requirements is set in stone. Think of it as a starting point for a conversation with the customer to try and firm those things up a little bit better.
That's a great suggestion. Thanks, Rick.
I'm going to jump in just super quick because I know we got another one to get to. I want to absolutely parrot what Rick said about customer needs. Usually the customer doesn't actually know what they want and or need. So always, 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 if you don't go back, if they give you 20 needs and you don't go back and ask 40 questions, reconsider. Always, always, always go back. And I know in this case, it would be going to the professors and asking, but I don't know if you've heard the old saying of, you know, what happens when you assume, you make a something out of you and me. So always, 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 you know, ask the customer. I would want to see, again, more on your costs. I think Rick stole my thunder on that one. Yeah, just the costs are quite high, and I would absolutely need to see a good breakdown of what those costs were. Because if you just come to me and say, you know, hey, we met all the other customer requirements, but we didn't meet this one and it was the cost, I may come back to you and say, well, that's just too bad because I literally only have $100 per square meter. Like, thanks for all the rest of your hard work, but I literally do not have the money. So cost breakdown, huge, huge thing, definitely would need to provide. Other than that, great presentation. I'm not an engineer, so I can't really speak on the diddly watts and the who things of everything, but the presentation itself was very good.
Thank you, Julia.
Okay, and I am gonna have to start the other. I do have a couple notes to say, but maybe I'll just slap them in email. And I will see you around. Good job, guys. Thanks so much. And thanks for all our external members for coming this early in the morning and lending us a hand.
Thank you all. We appreciate it.
Thank you.
Thank you.
Thank you.